Good afternoon, all. So in last class, we did some examples for calculating time complexity. And there we discussed these two important rules that if we have constant factors, we are going to remove those. Also, if there are any lower order terms in terms of n, so if you have something in terms of n raised to 4 plus something in terms of n cube plus something in terms of n, then all the lower order terms will not matter much because whatever is the higher order term of n, that will be the most contributions. Similarly, the constants, we can also look at it as something n raised to 0. So again, if something in terms of n is already there, then you don't need the constant terms. And by dropping those, we are going to get precisely all the, so we will have it something of this form, so which will fall into this category. So if we are most of the equations that we will come or most of the running times, we will fall into one of these 7 different categories. Now, when we are talking, so these are some examples how we look at log n, how we look at n log n. So maybe we can. So now here is a discussion of big O notation. So in other words, if you are saying if there is some linear function on, which is this is our classic linear function, which goes has same value, whatever the input value, same value in terms of time. So you will see that it crosses at points 1, 1, 10, 10, 100, 100, and so on. So it again depends upon the scale. It need not be exact same, but to represent it as it takes same amount of time or it grows with n. Now let's say if we have another function 3n, and then we have another function 2n plus 10. So if we start comparing these 3 functions, again they have shown a good comparison that when n is equal to 0, or I think this is at n is equal to 1, if I'm having linear function n, then my time is going to be n, which is 1. If you take the second function, which is shown by blue line, that function is 2n plus 10. So in that case, the time will be 2 multiplied by 1 plus 10, which is 12. So here you will see that it is starting some point higher than 10. And then third function is 3n. So if you calculate 3n for n is equal to 1, then the time will be 3 multiplied by 1, which is 3. So this is starting at 3. Starting point is 3. So you will see that at n is equal to 1, all the 3 functions have different value. But again, you will realize that when n becomes 10, then you will see that the value of 2n plus 10 and 3n kind of merging there. And then when you again look for higher values of n, maybe after n becomes 100, then you will realize that all these functions have same growth rate. So that's what we discussed, because if you look at it, all of them are in terms of n. So if we again use the same 2 rules, that we get rid of the constant factor, we get rid of this constant factor, then all these do represent linear function, which is big O of n. So irrespective of their constant terms or constant factors that we are adding. So here there is one concept of n0. So n0 is a point at which the growth rates merge. So here you will see that if we talk about the very first value, you cannot detect that what is the growth rate. So for example, if you look at the first 10 values of n, you will see that the growth rate of the 2n plus 10 is different than growth rate of 3n, and that is different than growth rate of just n. So at this point, for this particular, let's say, time segment from 1 to 10, you will not notice that the growth rates are same. Even more so for 10 to 100, also the growth rates don't look same. But after 100, we are having same growth rate. So N0 is such value after which you will see that change. So we are going to say there is a, and depending upon which function we are talking about, there will be a certain value of n after which the growth rates will start having, or the functions will start having same growth. Now for each function that will be different. Now here, the thing that we need to remember is even if it is 2n plus 10, even if it is 3n, even if it is n, for our purpose, all these functions are linear functions. Now here is another example. So if we take something in terms of n square, now if we again look at 100n, 10n and n, and if we are comparing with n square, then you will see that again till you reach at some value of n becomes 100, we will feel that, let's say 100n will grow faster than n square. So this is my n square. So if you pick value at 10, you will see that for n square the value is 100n, but for 100n the value is actually 1000. So initially when we start, we might think how come this is a linear function and this is a quadratic function, but because of the smaller value of n, until n will surpass this value, we are going to see that the growth rate of 100n seems to be higher for this particular portion because it is. But then when you go after 100, you will realize that the growth rate of 100n is lower than actually n square. So this was 100n and this is, I think, 10n. So after a certain point, again, we are going to realize that whatever is the linear function, the growth rate is same. So you will realize that whether it is 100n or 10n or n, all are parallel to each other. All the lines will be parallel, while the line having n square will grow much faster after 100n, because this was a constant factor. So after that, we'll realize the difference. So here, a kind of this C is a constant, again, the value that we can find. So here are some examples. Now we have to find out what is the big O for this example. What is big O of 7n minus 2? N. So again, we are going to get rid of this part. We are going to get rid of this constant. What is the big O of this example? N cube. So this is a lower order term. This is constant. This is also constant. So it is big O n cube. How about this? Log n. Log n. Yes. Okay, I shouldn't be writing. So all the explanation is already clear. So if you take some constant 7 and some value of n01, then after that value you will have same slope. That, the only thing we really want to know is these are the time complexities. Now, sometimes we have to compare two functions and we have to decide which function grows faster than which function grows slower than which function. Now, another thing again is we discussed this in the last class. but it is kind of counterintuitive. So we discussed three algorithms, and then that time we were discussing which algorithm is better. So if we have these three growth rates, we discussed A1, A2, A3. So if you have to find the growth rate, you will realize the growth rate of A1 is higher and growth rate of A3 is the lowest one. So actually A3 is the slowest growing function. A1 is the fastest growing function. But if you implement these functions, which algorithm will run fastest? If you implement these algorithms, which will work fastest? A3. Yes, so here it is kind of it goes counterintuitive, meaning that if whatever the growth rate, more growth rate equals to slower function, slower function. And if you have low growth rate, it means that that function is going to run faster when you actually implement that function. So actual implementation and growth rate it's kind of inversely proportional, because if it is taking too much time for me, it means it is going to be the slower implementation. Time is always our y-axis. So our y-axis is going to be time and our x-axis is n, which is our input size. So here, so these rules we saw. Now we are going to have some mechanism to compare the rules. So right now we are only going to look at big O, but there are some more symbols that we'll study after this. So when we are going to say Fn is big O of Gn, it means that the growth rate of Fn is always bounded by Gn. It means that the growth rate will never go above Gn. That is something when you show by big O. So when I say, so in other words, in terms of growth rates, we can also say the big O representation is kind of a less than equal to. Meaning that when I say I have a function 5n, I have a function 5n squared, let's say. Now we know that which function is going to have more growth rate, 5n squared. So we can, whenever we are going to say big O of n square, it means this function will not go worse than n square. So in this case, big O is also used in this manner. So let's say this is my fn function, and let's call this as a gn. So I can say that my gn is equal to big O of n square, because that for that function, I know it won't go worse than n square. Another thing is I can also say Fn is equal to big O of n square, because it is less than or equal to. So the left-hand side function can have lesser or equal growth rate than the right-hand side function. So technically, if I say Fn is equal to big O of n square, that is also correct representation, but it is not useful. So somebody just might say Fn is equal to big O of n raised to 10. Okay. So what information I'm gaining from this? I'm not gaining any information about how worse Fn is going, right? So most of the times, what we do is we go to the tightest bound, meaning that whenever we are talking about Fn, we are going to talk what is the exact function. So it is a linear function. So I will say Fn is equal to big O of n. Okay, but this big O generally works as a less than or also greater than. So Fn is big O of Gn means the growth rate is no more than Gn. In other words, it is less than or equal to Gn. So any this is true for any function whenever we define it by big O of any higher growth rate than the left hand side. So when we use big O notation, when we say Gn grows more, then we can say Fn is big O of Gn. That means either Gn will grow more or Gn will grow as fast as Fn. So it is yes. Can they have same growth? Yes, because it is kind of a denoted as less than or equal to. Can we say Gn is big O of Fn? So it means, can we say, so our Gn is 5n square, right? So can we say 5n square is big O of n? No, because whenever you say big O, it means the left hand side function has to have lesser or equal growth rate. So we cannot say Gn is equal to big O of Fn if Gn is growing more. But if Fn is growing more, if Fn has a more growth rate, then in that case, it's the same thing. We can say Fn is equal to, sorry, Gn is equal to big O of Fn if Fn has a more growth rate. So whatever is on the right hand side has to have more growth rate. And if they have same growth rate, then also we can say yes. But if Fn grows more, we cannot say Fn is big O of Gn. So kind of a comparison. Now, whenever the rules are similar to what we saw, so when we are having some Fn with polynomial degree d, then we always drop the lower order terms. Now the big O rules are similar to what we saw for time complexity calculation, and we are going to drop constant factor. Then we are going to use the smallest possible class of functions. So as I said, technically it is right. If anything which is higher than the left hand side, we can say big O of, but we will always use the closest function. So whenever we are talking about 2n, we will say it is big O of n instead of saying it is big O of n square, because this is also right. Now, again, when we have some value as 3n, we are going to drop that 3 as well. So instead of saying big O of 3n, we will never say big O of 3n. We will always drop the constant and we are going to say big O of n, big O of n square, or big O of n. In this case, again, we will not say 2n is. So technically, again, this is correct, okay, but it is not useful. So we are going to say the growth rate of 2n is linear. And that's how we are going to represent. So we will see, we are going to see a lot of so here are some, again, this, I think we discussed this when we were talking about the finding maximum example. So when we are doing the asymptotic analysis, so which is a theoretical analysis of how bad an algorithm can go. So that time I discussed with you that we are always considering the worst case scenario. So if there is a if statement, we are not going to consider that it might not even enter in that if. And so it will just take very few iterations, but we will consider what will be the scenario if there is an if statement. How many, in worst case, let's say we have a for loop, and inside for loop, which goes from I to n, we have some if statement, and we have some statements here. So ideally, we can assume that the if, let's say on an average, it is happening n by 2 times. But when we are calculating or we are doing the running time algorithm calculation, we are going to assume that in the worst case scenario, it is going to execute n times. So for every condition, it might go in the n. So that's how our assumption is going to be. And then accordingly, we are going to calculate. Always assuming the worst case scenario, not the best case or average case scenario. And then executed for the input size, so whatever our AN is, and then after we get some running time, let's say we get it like A10 minus 2. And then we are going to convert it into big O notation. So this is a linear function. By dropping constants, I get it as a big O of n. So now I'm going to switch to another book. So they have actually much detailed discussion on the notations. So I have posted it in the files. Here. So here, since I told you you can use any one of the books. So those are different chapters in different books. So if you are using the Goodrich book, it is I think chapter 4 for algorithmic analysis, and for Marquis it is chapter 2. So some parts are explained very good in this book. So typically the symbols, so different symbols for comparison. So we'll do that. Now homework part, I will come back. So I'm planning to post homework today, so which will be due not, I think not 7th, it will be 6th. So 6th is the next question. So the homework is based on time complexity. So it will 6th. And then we will have our quiz on the same day. So it will help you, or maybe it will prepare you well, I think. Or the next time that we can have. Either we can have it on 6th or we can have it on 4th. So I think it is better to have it on the due date, because by the time you do the homework one, you will go through the material. So I believe you will also ready for the quiz that we did. So let's have a quiz, and the quiz will be again in class and the last 20 minutes of the class. So the syllabus will be time complexity and review for quiz and homework. So both will have same syllabus. So once you are done working on the homework one, you will also be ready. Now this part. So in this case, we are also going to study some other notation along with the big O kind of we just saw. Now there are some more notations like theta, little omega, big omega, and they are going to help us to compare specifically when we have two algorithms, which one works better, or when we are comparing growth rates of two algorithms, then we can use each one of these representation. So whenever we are calling asymptotic growth, we are calling it, or we are naming it as a growth rate of an algorithm. And assuming that we have two different functions, fn and gn, we are going to compare these two functions. So we saw there might be three possible cases. So if we have one algorithm and second algorithm, either they will both have same growth rate, or Fn is faster or Fn is slower. So these are the only three possible conditions, and we have three different notations to show that. So here, this is a theta notation. Let's start with theta notation. So the very first notation is used to show same growth rate. So here we study three different things. So if it's growing with the same rate, it is shown as theta. So that means both functions, whether I implement fn or I implement gn, they both are going to have same time. Not exactly time in milliseconds, but they are going to have same growth. So the growth rate is going to be same, not exactly the size time. So if we are talking about, let's say 2n and 3n. So what will be the time if I plot my 2n graph? Let's say it looks something like that and 3n looks something like that. So what are the possible values when n is equal to 1? It will be 2 and 3. When n is equal to 2, it will be 4, 6. N is equal to 3, it will be, let's say, 6, 9. Okay. So you are going to see that the growth rate, if we plot here, then the growth rates are going to be same. So when that is the case, we can say that we can either say 2n is equal to theta 3n, because both have, if you calculate the time complexity for 2n is also big O of n, time complexity of 3n is also big O of n. So in other words, we can also say for this function 2n, it has same growth rate as 3n. Can I say the other way around? Can I say 3n has same growth rate as 2n? Yes, we can say that, right? So 3n also has same growth rate as 2n. So we can either say in this way. So if it is slower, if it is faster, so those notations will say. So the very first notation is theta, and we are going to use it when any function fn and gn has same growth rate. So one way to show it is fn is equal to theta of gn. Means they both have exactly same. So this you treat it as equality. The big O I told you to treat it as less than equal to. But this is exactly equal. And there is a formula for that. So whenever you take limit under where n goes till infinity, and when you divide the first function by second function, and the value you get is a constant number, then you can say fn theta gn. So let's see it in more detail. So there are three rules for the growth. So for theta, we have to have same growth rate. And again, as I said, the growth rate when n is small, it doesn't really affect much. So we are more interested what happens when n grows too much. And then we are taking the ratio of these two functions, gn. And after we take this ratio under this limit that my n is going to infinity, and if I get a constant number, then it means these two functions are same. So either we can say fn is equal to theta gn, because the growth rate is same, or we can also say gn is equal to theta fn. So as long as it is a constant, we can say that. So if you change the numerator by denominator, only the constant will change, but that is fine. So now let's take this example that my one function has growth rate 2n and my another function has growth rate 3n. Now this need not be necessarily time complexity. It might be the actual running time or the function. So when we are comparing these two, we are going to use this formula. So we are going to say limit under limit where n grows too high. What is the value I am getting if I am doing fn divided by gn? So the n will cancel out, right? And we will get a constant number, 2 by 3. If we want to check for the second, again it will be only the constant will change, 3n by 2n, that my constant will now become 3 by 2. So I can also say Gn is equal to theta Fn, because Gn divided by Fn is also 3 by 2, which is a constant. And for this, I can also say Fn is equal to theta, so which is already here. Okay? So this is a rule for theta notation, which shows that the growth rates are equal or growth rate same. So here the value of C is any constant. So that is fine. Again, here is another function. If you have 2n divided by 4n, you will also get a constant number. Again, similar example, if we have 3n and 10n, limit under theta, n tends to infinity, it will again give me a different constant 3 by 10, still constant. So that is one way we are going to check if we are asked given two functions, if they have same growth rate, then we are going to use this formula. Under limit n tends to infinity, we are going to divide Fn by Gn, and whatever value we get, depending on that, we find out whether they have same growth rate or one is faster or one is slower. So this is for theta, it's quite straightforward. We are looking for a constant number. Now, another notation which is called as a little o. So let me add few slides here. So another notation is called as little o, and it is generally shown smaller o than the big O. So this was the big O that we were discussing, right? So big O is shown as a bigger O. This is maybe capital and small, or this is shown as a little o. Now whenever it is little o, and then we just saw theta. So theta is this. So whenever we are talking about little o, you can treat it as a less than sign, meaning that whenever it is we show by little o, the left hand side function has always less growth rate than the right hand side function. So here equality is not included. Here big O, it can be less, it can also be equal. In theta, it has to be equal. So if you look at the big O notation really, it actually can be used whenever you can use theta. It can also be used whenever you can use little o. So whenever I have to say the left hand side function is equal to right hand side function, that time also I use big O. Whenever you are saying the left hand side function is or the growth rate is smaller, then also we can use big O. So kind of a both symbols, instead of both symbols, we can use big O. Hence, big O notation is more common. So you will see that most of the times we will see that they are using big O notation. Now, what is the definition of little o? So in little o, we want that one function is higher than another function. Typically, the left-hand side function, the growth rate is lower, and the right-hand side function, the growth rate is higher. Now, in this case, under limit, there should be a formula here. So in little o, the formula is whenever we are calculating limit, Fn divided by Gn should give us value 0. Because now let's see some examples of this. So in little o, so this is for little o. So under limit, because we are only concerned what happens when n grows larger, and if we take Fn divided by Gn, then we get value 0. Now, how let's take one example of this. So whenever we can say Fn is big O of Gn, that time Gn has to have higher growth rate. So Gn may be having a more power of n. So let's take one example where Gn is n square and f of n is n. Now, in this case, if we substitute it in this formula, it will be limit n tends to infinity, fn is equal to n divided by n square. So 1n and 1n square will cancel out. That will give us 1 divided by n. So whenever you will have a multiple of n as a denominator where n tends to infinity, then the value of 1 by n will tend to 0, right? So now, whenever this is the case, we are going to say Fn is equal to little o of Gn. The growth rate of Fn is always smaller than Gn. Again, here equality is not included. It is only less than. So big O is only less than sign. The left-hand side function's growth rate is smaller than right-hand side's function too. So similarly, it might be, so the right-hand side function is higher, so it will have a higher power of n. So always we are going to end up with some term in terms of n having in denominator. So when n tends to infinity, this whole term is going to tend to 0. That shows that we can use little o. Again, this is again one way to have comparison and check which one of the symbols are more fitted to use in each scenario. Now, what was the third symbol we saw? I think. So theta we saw little o. Now there is another symbol pronounced little o. There is another symbol which is called as little. So here are some more examples. So if you take again Fn as 3n and Gn as n square, then again you will have 3 multiplied by 1 divided by n. So it will again value will go to 0 as n goes to infinity. So here I think I plotted the Fn and Gn functions. So if it is 1, if n is equal to 0, what is Fn? It is 0. What is Gn? N square is also 0. When n is equal to 1, Fn is equal to 3, Gn is equal to 1. So initially you will see that Fn has, or Fn looks like Fn grows fast, but that's not the case. And then when n is equal to 2, Fn becomes 6 and Gn becomes 4. So 6 and 4. So still a Gn is at a lower side. Then when n becomes 3, it will, both will match, I think. Yes. So at value n is equal to 3, the first function 3n will give us 9. At the second function, which is Gn n square, that will also be 9. So they are going to merge at 9. Now, after this point, you will see that the growth rate of Gn is going to grow higher and kind of they will cross and the linear function will grow slower than function. So here, when n becomes 4, Fn is equal to 12, Gn is 16. n is equal to 5, fn is 15, gn is 25. So obviously now the gn is going to grow faster. Just now here, I think this was the n0. So at what point they merge? So they merge at point n is equal to 3. So this is our n0, after which point the real growth rate starts. Up to this point, what we are seeing, that is not the real growth rate of the linear function. Because it is a multiple of 3, it is going ahead of gn for that particular area. But then after that it surpasses 3, you will see that it shows the actual difference in the growth rate. That's why this is kind of the merging point where they both cross, and then we actually get to see which function grows faster. So hence all the growth rates we are considering n grows up to infinity, not for smaller values of n. Those are not really meaningful. So this is also, I think, I brought it. Now, this is another symbol which is called as little omega, and it is shown as little omega. So you know little omega and big omega, right? So we are using again little omega, and little omega is shown as greater than symbol. So whatever is the left-hand side function fn, that has a higher growth rate than the right-hand side function. So little omega is a faster function. So whenever I say fn is equal to little omega gn, it means the growth rate of fn is faster than gn. So you can also remember it as a greater than symbol. Now, what is the formula? How are we going to find that? So again, we are going to take limit when n grows too fast and fn divided by gn. So whenever fn has a more or its growth rate, it will have something in terms of n. And when n tends to infinity, it will automatically tend to infinity. So this is the whenever between two functions, the relation will give us over limit. If it will give us infinity, it means fn is little omega gn. Okay. So let's, I think this is one example we can take. Fn is equal to n square and gn is equal to 3n. But that, I think that's not. Fn should be faster than gn. So let's take it on the next slide. So Fn is equal to 3, because here we have to show if we can use the omega notation. So the growth of Gn is 3n. And under limit, we have to again take Fn divided by Gn, but that should this time give us infinity instead of 0. So now, even if you don't know all the limits, don't worry. It's not that we are not going to do any other computation than just finding is it 0 or infinity or it's constant. That's the only thing we are going to do. So you need not really remember all high school algebra also. So n square and divided by 3n. Here again n will get cancelled out, and we are going to say there is 1 by 3 and then there is n. So as n grows to infinity, this value also will go up to infinity. So that means fn has a higher growth rate. And in this case, we can say fn is a little omega g. So this means this growth rate is a greater growth rate than g. Now I think we are done with most of the comparisons. So sometimes we can also see examples compared to functions n and n square. So if we take n and n square, then obviously we know that we can say that the n is equal to little omega n square, right? So this is less than symbol because it is little omega. We can also say n square has a higher growth rate than n. Both are correct because it is a little omega. So both are correct representation. So whenever we say Gn is little o of Fn, we can also say Fn is a little omega of Gn. So both represent the same thing. So whenever we are saying Gn is slower than Fn, it means Fn is faster than Gn. Now I think we are left with where is the big O? Big omega. So like big O, there is a big omega notation. This is called as a big omega notation. So maybe I will create a summary like table that will be easier to see. So big omega is just like upper bound. So we did this, we consider that Fn has growth rate slower or equal to Gn. In omega, it is greater than or equal to. So you can say Fn has growth rate greater than or equal to Gn. So here for big O, it was less than equal to. For big omega, it is greater than equal to. Again, if we have to show it, we can also show. We can also show. So this is a last symbol which is called as big omega. And again, it entails two representation, either Fn growth rate can be greater than Gn or Fn's growth rate can be equal to Gn. So again, we cannot say Fn equal to Gn. That is technically wrong. So I add equal to, or this is equal to, we can also say theta, right? So both again both theta and, sorry, this should be omega because it is greater. So both symbols, whether the function Fn can be greater, having greater growth rate or having same growth rate, we can show both the representation by big omega, just like big O. So in big O, we also show equality. We also show that the left-hand side function is having less growth rate. Here we are showing the left-hand side function has a more growth rate, or is growing at a faster rate, or it is growing at the same rate. So that is a big omega. So let's take some kind of examples where we can check if we can say this at all. Then we know if we really understand. I have to rearrange this. Okay, let's go through this problem. They are pretty straightforward. So n squared is equal to big O of n squared. That is true because both the functions are equal. 2n is equal to big O of n squared. Is it true or false? So I already have answered there. So we can say like this, because as long as the left-hand side function is less or equal to right-hand side, this is also true. Then if you say n is equal to big O of n squared, that is also true. We can say that. Can we say n square is equal to big O of n? No, that is false. Can we say 2n is equal to big O of n? Yes, both are a linear function. So we can say, can we say n is equal to big O of n? Yes, we can say, right? N is a linear function. Now, can we say n square is equal to theta n square? Yes, because theta represents equality, right? Theta is equal. Then, can we say 2n is equal to theta n square? No. Both has to have same growth rate. So on the right hand side, it is n square is a higher growth rate. So we cannot say that. So this is a false statement. Now, can we say n is equal to theta n square? No, that is also false. Can we say n square is equal to theta n square? That is also false. 2n is equal to theta n, that is true. N is equal to theta n, that is also true. Then I don't, did I have some for omega? So here are again some examples. So if something is there like n plus 5, and we know that if we have to find out the time complexity of this, it is closest to big O of n. So we can also say that it is theta n, because this is a linear function, and if you discard the constants, then this is also linear functions. So in other words, we can say n plus 5 is equal to theta n is also equal to big O of n. It can be equal to big O of n square. It can be equal to big O of n cube. It can be also equal to big O of n raised to 5. So all are correct because big O is less than equal to, right? So technically all are correct, but they are not useful. Big O of n is the most useful. So we are going to use big O of n. So kind of this is also called as a tightest bound, where we are going to go with the value which is closest to the original function. So if you are talking about n plus 5, so plus 5 is a constant. So it is essentially comes down to be some linear function in terms of n. So we can represent it in different ways. Then inverse of big O is big omega. We can also look at it because this is less than equal to, this is greater than equal to. So if Gn is equal to big O of Fn, it means F. So when we say Gn is equal to big O of Fn, it means Gn is a slower function. So in other words, we can say Fn is equal to big omega of Gn, right? So any numbers, whenever we say 3 is less than equal to 5, we can say 5 is greater than equal to 3. It's exactly same thing in terms of growth functions. But now we are using different symbols because we cannot technically say that they are same function because they might not be. So sometimes if it is 3n and 5n, we cannot say they are equal to or they are less than equal to. So in that case, we want to use these symbols. So even though they are not equal in terms of time, the growth rate is still equal because they both are linear functions, and that we are going to represent with big O or big omega. I think that was this class. So here are some more rules when you go to programmatically. So the rules are now regarding how we have to find the time complexity. Sometimes it might be the case that you have a program in which, let's say, for some part, so how to, maybe I will give you one. So let's say, we are starting a function like last time, and then for some part, let's say we have two for loops going 1 to n. And then I'm also doing some other thing inside this function. And for that function, we have 3 for loops. And again, each going 1 to n. Now, if you look at what is the time complexity of this program. So for this particular code, the time complexity is big O of n square. For this, it is big O of n cube. So what is the time complexity of this? N cube. So that's the first rule. So whenever there are two different time complexities, you always take the maximum out of this. So again, kind of it relates to the worst case scenario, right? So whenever that's the case, you don't do plus. So we are not going to do plus. Instead, we are going to take whichever one is maximum. That is our time complexity. So again, here some examples. If we have n square plus 10, we are going to take big O of n square. 50 n cube, 45 n raised to 5, 60 n 100. Our time complexity is going to be n raised to 5. Doesn't matter if other module has 50 n cube, other module has 60 and other module has. We are going to pick the maximum. Now the second rule is sometimes whenever you are doing it inside one loop. So there's something similar we also did for loops. If we are doing one for loop and inside that we have another for loop, then that will be essentially the multiplication of both time complexities. So if we are talking about there is one loop or one program which has 10 raised to n square and another program inside that same function having 10 raised to n square, then total we are going to multiply both and find it as n raised to 4. So when actually we are doing one for loop inside another for loop, we are also multiplying if you look at it. So n multiplied by if third for loop is running n by 2, we are multiplying it that way. So if it is one inside another program, then we are going to multiply the time complexity of both. Then if it is a polynomial of degree k, then obviously whatever is your time complexity is going to be n raised to k. Now another thing is if for any it grows in log n value and that k might grow, so might go from 1 to let's say 10 or 100 and it is n, then in that case, whatever value we are getting, it is still bound by log n, meaning that it will not go worse than log n. So if you have log to some power and n, you can still say it is big O of n for any constant value. Those are some rules for, so these we already saw. So next time, I think we will see some more examples of the notations. And I believe now you should be able to do the homework 1.